Okay, so now I'm going to talk about problem 3.56 out of the book, which was number 17 on our chapter 3 homework. This is the hot air balloon problem. Um, so the situation is you've got a hot air balloon taking off from the ground and is accelerating upwards. It's got a magnitude of acceleration of g over 4. So that means that the 9.8 meters per second squared that gravity causes an object to accelerate downwards, the hot air balloon is accelerating with about 2.5 meters per second squared upwards. And then after some unspecified interval delta t, someone releases a sandbag from the basket, and presumably the sandbag is going to fall to the ground and it's going to hit the ground hard. But the problem is saying, well, how many seconds will it take the sandbag to reach the ground from that moment after it starts to fall? So this is pretty interesting, and it's a little bit tough for us because we haven't done very many that are so abstract. We don't really have numbers in this problem. We have an upward acceleration that's 1/4 of the acceleration that it would have if it were falling downwards. And we've got a time interval that's not specified numerically. And the answer that we're going to express is going to be in terms of delta t. So that means that we're going to be eventually coming up with an algebraic expression for how many seconds it takes to fall to the ground, depending on how many seconds you allowed it to rise up before you cut the sandbag. So I am going to first solve this using Desmos. I'm going to do it graphically and try to make it a little bit more concrete. And then I'm going to go back and do it in the equation way. And of course, solving this in Desmos is going to involve a fair number of equations anyway. So here we have a blank Desmos graph. And I'm also going to use this to kind of illustrate the way I use Desmos as a tool and also how to think about these problems. So first, I know that on the way up, that balloon is accelerating. And I know that it's accelerating with a constant acceleration. So I know that as it's ascending, it's going to acceleration during phase 1 of g over 4, whatever g is. And g is 9.8. So we'll put some numbers in there. I'm just defining some constants here. So the acceleration on the way up is g over 4, and g is 9.8. Cool. I also know that if an object is experiencing a constant acceleration, that I can always describe its position at some later moment of time using a function of time that says there's an initial position plus an initial velocity times how much time has happened, plus a term that describes what happens due to the acceleration. So we've got the initial position plus the initial velocity times time plus 1/2 the acceleration times the time squared. And you notice that I'm using x as my variable standing for t, and I'm using p to stand for position. And I know this is confusing because we usually do our equations by hand using t for time and x for position. Desmos is, I find, a little bit unhappy if I use t that way. So we're using x to stand for time here and p to stand for position. All right, now it's pointing out to me I don't know what the initial position is, and I don't know what the initial velocity is. But it's offering, would you like to make a slider for those? Okay. Oh, interesting. Well, let me put this in projector mode so it's easier to see. And I notice that if I change that initial position, that moves this parabola up and down because it's changing the x-intercept that it starts from. And if I move the velocity around, then it changes the initial velocity. It's basically, so it's saying initial velocity 2.6, that's changing the slope at the intercept. If I make it steeper, that makes it steeper at the intercept. If I put it on the other side and make it negative, that means it's pointing downwards at the intercept. All right, but for this problem, the balloon is accelerating from the ground, so I can set the initial position to 0, and I can set the initial velocity to 0 too. Cool. So this function is describing the position of the balloon at later moments of time, given the acceleration and the initial velocity and position. All right, well, this part of the graph doesn't really make sense, this negative part, because the balloon didn't start earlier and like go down and then come back up again. It started on the ground and only went up. So I'm going to restrict this to only be positive values of x. I want x bigger than 0. Cool. That's on the way up. So now what? I want to do something to show how high it gets before they let go of the sandbag. So I'm going to try and make this, like I said, like slightly more concrete. Oops, wrong slide. I've got the delta t right there. So I'm going to represent how much time it's ascending as a variable. So I'm going to say dt is, let's say, 5 seconds. Just make up a number for it. And then that means I can make a point, dt, comma, p1 of dt. This is how I'm representing delta t. Where is my point? There it is, way up there. So this is saying, given these conditions, after 5 seconds, the balloon would be 30.625 meters up in the air. That makes sense. That's plausible. So let's do something a little bigger than that. Let's say it's ascending for 10 seconds, and then I'm going to change my scale. So this is a little bit easier to see. So I want the x scale to be like from -2 up to 20. That's good. So that'll show 10 seconds on either side of the time when the sandbag falls. And then I want the y-axis to go up to, let's see how high I need to go, -10 up to 100. Is that high enough? Nope. 200. Ah, there we go. Great. So we can see that after 10 seconds, that balloon is 122.5 meters in the air, given the acceleration of g over 4 and the initial position and initial velocity. That's great. Okay, well now I should start thinking about how to connect this up with what happens after the sandbag is cut loose. So basically, I want another position function that will describe what the sandbag is doing after it falls. So let me just put in variables to represent that. Position 2 at time x is the initial position for the second part, plus the initial velocity for the second part, plus 1/2 the acceleration for the second part, times the position squared. Okay, and now it's telling me I don't know what the initial position is, or the initial velocity, or the acceleration. So I'm going to make sliders out of all of them, and we'll figure out what they are. Okay, let's change the color of this so that we can see it better. So red will be after it falls, and green will be on the way up. And you can see this parabola, it doesn't match up at all right now because I don't have the right initial position or the right initial velocity or the right acceleration. None of those make sense. So let's set the acceleration because that's given to us in the problem. It's falling on the way down. That means the acceleration is going to be -g. So I can set this to be a2 on the way down is -g. Now I have a parabola that actually points the right direction. It's downwards. That's cool. But the starting position and the starting velocity aren't right. So how am I going to figure out the starting position and the starting velocity? Well, the starting position is that spot right there. That is the location that the balloon was at when the sandbag was cut loose, which happens to be at time delta t, which I've made to be 10 seconds. So I can get that by plugging in the value of delta t into that original function for the position. So I'm going to say x initial is p1 of delta t. Aha! That's cool. So that made it rise up. So the initial position is the right value. Oh, why is it saying 123, not 122. Oh, it's because of that VI equals 1 right there, because I forgot to multiply by an x here in that equation. Oops. Yeah, so initial position plus initial velocity times time plus 1/2 a time squared. Okay, now I need to figure out what the initial velocity was so that it has the right slope at that moment. Now, this is really interesting. Let's think about what the sandbag is going to do after you cut it loose. Is it going to immediately fall from there? That would make the graph look like that. Or is it going to be flat and then start to fall? That doesn't really make sense either, because that would suggest that the velocity is instantaneously changing from the value that it had on the way up to some other value. And that doesn't happen. Acceleration so the acceleration does change essentially instantly when that rope is cut holding the sandbag on, but the velocity doesn't change instantaneously. It needs to take some time to change because that acceleration has some time to act, which means that what you're going to see is that the velocity right here on this side of the sandbag dropping is the same as the velocity on that side of the sandbag dropping, and then it's going to turn around and come back down. So whatever the velocity is at that moment just before, the velocity for this other graph should match that, which means I can figure this out by saying, well, what's the velocity of the balloon at that moment just before it let go? Well, I know how to figure that out. I've got an equation describing velocity, how the velocity changes. I have the initial velocity plus the acceleration times the time. So the velocity that it starts with is going to be the velocity that the balloon started with on the ground, which was 0, plus, plus the acceleration of the balloon on the way up, times how much time it was ascending, which is dt. There we go. That looks right. It's got the right kind of slope. It's got the right starting value, and it's got the right kind of slope so that this looks like it will match that. Now I've got one more problem, which is that this function doesn't seem to be in the right place. That's the point that I want, and I want it to be over here on top of that spot right there. And that's because this function is saying is treating time 0 for the second part of the trip as being the same as the time 0 for the first part of the trip. I think that's probably going to be kind of confusing, so you should think about that a little bit, what exactly it is I'm saying and what we're talking about here. Basically, I need this point to move there so that the velocity and the position right before the sandbag lets go match the velocity and the position right after lets go. So this red will take over from that spot. So I need to do a transformation. So I'm going to make another function that is a shift to the right from that red one. So I make it shift to the right by subtracting the right time from it. And there it is. So you can see this red one had the right slope in the right position, but it needed to be moved over to here. So now it matches. And if I zoom in on that a little bit, you can really see the slope just before that point is the same as the slope just after that point. And then that sandbag keeps going up for a while, hits a high point, and then begins to fall again. I know that's counterintuitive for most people that they should do that. So let me change the color of this to red. No, I'll leave it as blue. So this blue is the correct one. The green is on the way up, the blue is on the way down. And then I'm going to restrict this so that it only shows it after that time delta t. So I want x has to be bigger than dt. There we go. And now you can see the balloon is going to ascend. It's getting faster and faster. The sandbag is going to cut loose. It's going to initially have the same velocity that the balloon does, and then it's going to slow down because gravity is now acting fully, not counteracted by the lifting force of the balloon. It's going to get to a high point of apparently 153 meters, and then it's going to start to fall again. So all of that there describes the position on the way up and the position on the way down. And you can see that if it took 10 seconds to get up to the spot where it begins to let go, it takes 18 seconds total to fall back down again, which is 8 more seconds after that moment. And I'm going to do another video where I do the algebra to figure out exactly what that is. So basically the question is asking, given this time, how much more time does it take to get back down to the ground? And it wants it to express it as like a ratio. So this is 0.8 of that amount of time, roughly. And two more things I just wanted to show you real quick as part of just to show more of what Desmos can do and why I love it so much. I'm going to put in the answer for that ratio as a point. So the time when it hits the ground is dt plus dt over 4 times 1 plus the square root of 5. See that 18.09? That's the same as that 18.09 right there. That's cool. And then if I put it in parentheses like that with comma 0, it makes a point right there showing that's the moment it hits the ground, and that's the moment where the sandbag lets go. And then the other cool thing that I can do is I can drag these points around to say, okay, let's imagine that it was 5 seconds before they let go of it. Then it's going to be 9.117 seconds from the beginning when the sandbag hits the ground. Or make it move up to there. So if it's 12 seconds before it lets go, then it's 21.7 seconds when it gets back down to the ground again. So very cool. Definitely, I want you to think about the physics of this problem. The insight is we've got a constant acceleration up. We have a continuity of the velocity right here at the spot where the sandbag lets go, but the acceleration is not continuous. So the acceleration suddenly changes right there. You can see the inflection, but the position, the velocity is continuous, and the position is continuous. And then that velocity begins to slow down and turn around and then come back down to the ground again. And then in the other video, I will show you how to do the algebra to get what exactly that ratio is between that point and that time.